would be in milliwatt. So I will directly take the log and multiply by 10. Conversely, you can't get the received power in watt, but then you multiply it by 1000 and take the log and then multiply by 10. So I would say that the power transmitted is 1000 milliwatt. 1000 milliwatt is 1 watt. Right? So this is 1000 here, milliwatt, multiply. Gain of the transmitter, 1. So what kind of antenna is this? Isotropic, spherical, ideal antenna. The gain of the receiver is 2. So maybe this is an omni antenna. And we have the wavelength. What is the wavelength of the system? We don't know. We have the frequency. So the wavelength is C over F, 3 multiplied by 10 or 8 over 9 multiplied by 10 to power. This is 6, this is 2, so this is 8 also. This goes with this, 3 over 9, and this is 1 over 3. Meter or centimeter? Meter. Why meter? Because this here is meter, 3 by 10. Okay. So it is 1 over 3 squared. 4 squared is 16, pi squared, and then we have d squared. What is the d? D is 5 kilometers. So what should I put here?
Should be 500 meters.
Should be in meters. Why should be in meters?
Because the
Because the wavelength is in meters. So they should cancel each other. So, sorry?
The power is milliwatt.
We don't care about the power. This is distance. This is distance. They should be the same unit, so they will be cancelled. All the units should be cancelled except the power unit, because the left-hand side here is a power unit. So whatever units you have here should be cancelled. Notice, this is unitless. This is unitless. This is square meter. This should be square meter. This is unitless, and this is unitless. So the only unit left is the milliwatts. And so the received power will be in milliwatts. So the distance should be 5000, right? Square multiplied by L. What is L?
1.
1. And hopefully if you do the math correctly, you will get 5.6 multiplied by 10 to minus 8. What is the unit?
Milliwatt.
So the power received in dBm equal to 10 log this value, 5.6 multiplied by 10 to minus 8, and this will give you minus 72.5 dBm. Okay, that's typical question that usually encounter in exams, and it included maybe everything. Now we have gains, we have unit losses. Maybe, for example, in the problem, I will tell you the hardware losses is more than 1, right? So I will tell the hardware losses is 1.25. So you just plug it in. That's it. So anything changes, it's just the numbers. But the concept should be very clear now, right? We have a transmitter power, we simplify it by having gains, and then it will be dropped over the distance because of the propagation, right? Over this distance, and then it will reach to the receiver. I want to comment also about this equation, and generally related to the other parts of our course. Notice here something important. Let's discuss the received power here. The received power is proportional to the transmitted power, right? If your base station transmits more power, you will receive more power. That's intuitive. But also, it is proportional to the gains. Sometimes you are limited by some transmitted power. You cannot increase it, maybe in mobile phones or something like that, okay? Because of the limited battery life, for example. You can't compensate by that. You can minimize this and maximize this, right? You can minimize the power of the transmitter by changing the shape of the transmitter so that you have more gain. So the receiver will receive more power for the same transmitted power. Also, you can minimize the distance, right? Intuitively, if you make the distance very small, you will receive more power at the receiver. But also, you can maximize the wavelength, right? So if you don't change anything, you just change the wavelength or the frequency in this case that you are working on. If you increase the wavelength, what will happen to the power received? It will increase. In increasing the wavelength, it means for the frequency, you reduce the frequency, okay? So you use low frequency, a kilohertz for example, or a few megahertz, right? And you can actually serve larger distance. Because the received power will be higher at a given distance, it means now the receiver can go beyond this typical distance. So you can increase the range by increasing the wavelength or decreasing the frequency. And that's why in radio telecommunication we don't use very, very high frequencies. We use something in 900 megahertz, maybe double that, but you don't go to the 100, for example, gigahertz. Except nowadays, people started to talk about this. But let's go to 100 gigahertz, 200 gigahertz, 300 gigahertz, and this is called millimeter waves, right? So now, one advantage we understand of the millimeter waves, very high frequency, what will happen to the wavelength? Very small. Even in free space, the received power will be very small, so the distance of the cell or the size of the cell will be shrink. But that's no problem because in 5G we want that. We want to shrink the cell size, so maybe now we can go beyond the typical frequencies. So this first equation, just by looking at it, it really teaches you a lot of concepts in design of telecommunication system, especially the relationship with the wavelength. So any question about this problem here? Did anybody try to solve it? Okay, another question. Can we solve it directly in DBM? Can we have an equation that gives me this number directly without going into the original first equation? We can. The received power, you can just calculate this in DBM. Then the received power will equal to the transmitted power plus the gain in the transmitter, because multiplication with the log it will be plus the gain in the receiver, minus the losses, whether it is in a free space or in the system. So now you convert the multiplications into subtraction and addition, but make sure everything in dBm and everything in dB, if you want to do that. So two ways, and you can try the other way, and you'll get exactly the same number in one line. If you don't like that, you can go back to the Friis equation, plug your numbers, but the Friis equation will not give you result in dBm. You need to convert it at the end to the dBm. And since dBm works with milliwatt, it's better to use the transmitted power in milliwatt. Okay. Now, one question I must ask you is what is the total path loss for the system in dB? So what is the loss in dB? The loss, power transmitted minus power received. Okay, I want the loss, and this equation means that the loss will be calculated in dBm. So what is the power transmitted in dBm? So I will say, so you don't forget this is dB, this is dBm, and this is dB. These are the units. So what is the loss in the system? The power transmitted. What is the power transmitted? Is 1 watt. What's 1 watt in dBm? 1 watt is 1,000. So it is 10 to the power 3. Log of 10 to the power 3 is a 3. Because it's just simply the 3 will go to this side. Then 3 by 10 is 30. Minus the power received, what is the power received? We just calculated, which is also negative, minus 72.5. And this will be 102.5. Right? So remember, the loss is a positive number. Usually the transmitted power is a positive number. Usually the received power is a negative number, because we have said that, for example, 30 dBm, meaning 1 watt. 1 watt is really high power you are transmitting. But notice, the power reduced from 30 dBm above 0 to minus 72. So this is a fraction number in watts, very small number, about 7 zeros or 6 zeros, and then number 7.000, then 7, very small number. And this is only in free space. We didn't touch Hata model, Lie model. This is only in free space. So always when I ask you about the loss, use this equation. Power transmitted minus power received. Usually you have the power transmitted as part of the inputs. You calculate the power received and you subtract them. Okay. So I can remove this now. And the other part of the question, using the parameters of problem 1, so the same input, calculate approximately the loss exponent V. For large city, assume a base station, base station height of 140 meter and mobile unit antenna height of 1.7. Okay. So now we are moving from free space to a large city. What will happen to the loss? Will it increase or decrease?
Increase.
The loss will increase. So since we got in free space 102, right? 100, 102.5
dB.
dB. So about 100. Now, even before solving the problem, as a rule of thumb, we should anticipate even higher loss. So if we solve the problem and we get lower loss, we mess something. So there are some rule of thumb you can use so that you check generally your answer when you answer these questions. Okay, what is the loss exponent V in free space? What's the value of V in free space?
2.
2, right? Can we go lower than 2? No, this is the minimum value because of the square of the surface area that we talked about yesterday. So this now in a large city, so we should expect, when we calculate V, we should expect a larger number. We get less than 2, it is a problem. We get 2, it is a problem. Larger than 2, it means maybe you are in the right direction. So another rule of thumb that you can use to anticipate when you finish your computational efforts and you've got the number, the number should make sense, right? Okay. Usually in the exam, I will specify the model used, so I will spare you thinking about whether I use Hata model or Lie model, etc. So I tell you, for example, use Hata model to calculate the density. But here it is very clear we need to use the Hata model because the exponent V we discussed as part of the Hata model, not part of the Lie model, right? So
this change will be in the exam.
yes, you don't need to remember this equation. Take them to the exam and everywhere else if you need it. Okay. And but you see, I didn't include the first equation because it is a simple equation and the basic equation, and we even derived it, right?
Can I have it for the exam?
You made the first equation.
Yeah.
No, but you will disappoint me because we have derived it. We didn't derive this equation. So you can, even if you understand the concept, you can re-derive the whole equation. So I hope you remember the first equation. And I promise you in next courses, if we have the chance to take it, I will give you a larger cheat sheet. Okay. So we need to calculate V, right? So let's remember what is V. This is V, right? So V, to calculate it, you need the loss dV and the distance d. You need this one. And this you get it from the atom, based on the information that I supplied in the question. Minus the power loss at d reference. And use this equation, which is basically free space propagation equation. So the second part, P loss at d reference, we calculate it from this equation based on the inputs. So now we have these two numbers, we subtract them. And then we divide by the log at distance and log at d reference, and of course these numbers you would know about, the d and the d reference. If you do that correctly, you get the exponent V. So the longest part maybe is do the Hatta model. Okay. So what are the new formation? What the new formation we have now? So this is power received in free space, right? And we have a new information, which is the height of the base station, which is 140 meters, and the height of the mobile unit, which is 1.7 meter. Okay. And let's remove this. So now we know that this is 1/3. Now the first part is to calculate this loss according to Hatta model. And according to Hatta model, this is the equation we use. Right? So this is the loss at the distance d. 69.55 plus 26.16 log the frequency, which is 900 megahertz. And remember the frequency according to this sheet, this slide here, the frequency you always put it in megahertz, the distance in kilometers, the d. Okay, so now we put log 10, 900 here. 44.9 minus 6.455 log height of the base station, which is so 140, right?
140, yes.
140 meter. Log d, and the d is the separation distance between them, and the separation is 5 kilometers, right? So it is 5. Minus 13.82 log hp again, 140 minus a of h mu. And I said large city, so it is the first equation, which is this one. So now we know what is the first thing we need to calculate, right? It is this one, a h mu. So AHMU equal to 3.2 multiplied by log 10, 11.75 HMU, and this whole log is squared minus 4.97. Okay, so we just need to plug our numbers, 3.2 log 11.75 multiplied by the height of the antenna in meters, which is 1.7. All squared is 4.97. And if you do things correctly, you should get this number, 0.442. Okay. Now we know A, we can go to the power loss equation and calculate the power loss in dB according to Hata model, which is 69.55 plus 26.16 log the frequency, and frequency is 900, so log 900 plus 44.9 minus 6.55 log multiplied by log the height of the base station, which is 140. Right. All this is multiplied by the log of the distance, and the distance is 5 kilometers, and we should write 5. So here log 140 minus 13.82 log the distance again, which is 140, minus AH, and AHMU is 0.44. And this will give you 138.2. What is the unit? D. Because this is a loss. Now, what is the last number we got? Okay, finish this one. Yes.
The distance is 5 kilometers, but why is 5?
Yes, so we said when Hata did his model, he chose his units. Right?
Oh, yeah.
So here we said that the frequency should be in megahertz. The distance D should be in kilometers. So if I tell you 5 kilometers, you just put 5. The antenna height of the base station and the mobile station, obviously in meters, and we should remember that. So maybe I will try to trick you, give you this in kilometers, but then you need to plug the meter variable. Okay? And these unitless numbers in the beginnings are all because of these conversions. So maybe the original, when he started his model, this was in meter. Then he take the 1000 out, and he take the log of that. So this 30 and add somewhere there. So now you should plug it in kilometer. You don't need to care about that. We just need to remember our units. Okay. So what is the loss in this large city? 138. What was the loss in the free space? At the same distance, basically. 100. So now the loss has increased from 100 or 2.5, right? 102.5 to 138. It might seem small in dB, but remember, each 3 dB is doubling. Each minus 3 dB is halving, right? So each 3 dB down, you halve the power. So if it is 6 dB, you divide by 4. If it is 9 dB, you divide by 2 by 2 by 2, 8, etc. So this is really a huge increase in path loss in this city. But we are not done yet because the question was about calculating V, the exponent V. And to calculate the exponent V, Hatta model is not enough. We need to calculate the path loss at the reference distance. And if I don't give you the reference distance, the default value is
100.
100. So now let's calculate the path loss at the reference distance. So the loss, path loss at the path loss at the reference distance, T reference, is 10 log by D reference over lambda square, and all this will be square, which is basically the original loss equation that we have encountered, the second equation, minus the 20 log lambda over 4 pi d, plus the 20 we have factored into 10 by 2, we took the 20 here, then we flipped, then we have the minus sign, multiplied by the minus 10, and we get 10 log. So even if you don't remember this equation, if you remember that's the minus 20 log lambda over 4 pi d, it will give you the same answer. So now, 10 log 4 pi, what is the D reference? The reference distance,
100.
100 meter square over lambda square. What is lambda? 1 over 3. So 1 over 3 square. So you can see this is in meter. Squared meter squared. This is meter, squared meter squared, meter squared with the meter squared, and we get rid of all the units. Okay, and if you do this, you get 71.52 dB. So that makes sense because in free space, at 5 kilometers, we got about 100, right? Now we reduce the distance to 100 meters, and it is 71, less than the free space loss at 5 kilometers. So now we have this number, 71.52. We have this number, which is 13.82. Now we can calculate V easily. So V is the loss according to Hatta model in dB minus the loss in free space. Let's just call it loss at the free space at the reference over 10 log D minus log D reference. And this equal to the Hatta model loss is 138.2 dB minus the loss at the reference distance is 71.52 over 10 multiplied by log. What is the distance? It's 5 kilometers. So do we put 5 kilometers or 5,000 meters?
5.
5 kilometers or 5,000?
5,000.
5,000.
Who says?
5,000.
How many people says 5,000 meters?
I say 5.
5,000 meters, not 5 kilometers, not number 5.
I say 5.
You say 5. Okay, both of you are right. And we'll see why. D, if you choose it in meter here, this one should be in meter. If you choose this in kilometer, this one should be in kilometer. So since the reference distance we use 100 meter, so here use
5,000 kilometers.
5,000 minus log 100 meter. Now why I'm saying this? So what I'm claiming now, log 5,000 minus log 100 is equal to log 5 minus log 0.1. Is that true? Yes, it is true, because 1,000 here and 1,000 here is the same number. I'm saying that this one is the same as, so this is a side note, so log 5,000 minus log 100, I'm claiming this is the same as log 5 kilometer minus log, the reference distance in kilometer is 0.1. Why? Because if I want to convert this to the meters, I multiply this by 1,000, so 10 to power 3, right? By 10 to power 3. And this I multiplied by 1,000, and we know the multiplication of two variables is the summation of the logs of them, right? So it will be log 5 plus log 1,000 minus log 0.1 minus log 1,000. So the log 1,000 will be cancelled with the log 1,000. You can check it in your calculator. So make sure that these two units are the same. And if you do that, you will get 3.92. So now the exponent is 3.92. In a free space, it is 2. So now we have a lot of losses. So I just wanted to show you this. So now you can see log 5,000 minus log 100, okay? So let's remember it is 1.69. Now I replace it by log 5 kilometers minus log 100 meter in kilometer 0.1 divided by 1,000. The result was 1.69 and 1.69. You see? So we just need to remember that this one P loss, here the D in, this is from the Hatta model, and the Hatta model accept a distance of kilometers. And the P loss are the D reference. You can use whatever you like, but make sure the D reference is the same unit as the wavelength. So if the D reference in meter, the wavelength in meter. And if you use the D reference in meter, make sure the D here should be also in meter. so we have maybe 5-7 minutes left, and if there's any question. Okay, so no questions? So I hope this means that we understand the basic concepts here. I think it is not, maybe at the beginning it was, seems difficult, but now we just have one equation, which is in free space propagation. For this equation, we can calculate any power parameter in free space or at reference distance. We just added more complicated equations, and for the harder model especially, when you move to cities. This equation you don't remember them, you just have to understand the concept and the units, collect them, and you get hopefully the right result. And these are the typical questions you would expect in your exam. Calculate the receive power, the loss in your system, the exponent, etc. Thank you very much.